Hey, what's going on, guys? KIM here. So I've connected KIM-1 ROM to my 6502 CPU emulator written by Mike Chambers that I've adopted to run on Arduino. And ROM is also going to prog-mem, obviously, because otherwise it just wastes, it not only wastes the entire RAM, but it doesn't even fit into RAM because only 1K of RAM for Nano and Uno Arduinos. 8K for Mega that I'm gonna be using later on, but again, I'm just debugging on Nano because I want to make sure it runs on the minimalist setup, and then obviously the extensions are possible. So let's kickstart by demonstration, and then I'll try to understand what's going on here, walk through the source code, and try to highlight the most important things that I made. All right, so I'm going to the serial monitor. So let's clear the output. And I just hit the reset button on my Arduino Nano, and here we go. And you might be wondering that nothing special in seeing these addresses. However, it's not so, well, at least for me. So what in particular this means, and let's make it always on top as well. Let's just go to the source code within the editor. It's just easier way for me to consider. So yeah, the RAM initialization just goes from the previous part. Doesn't mean much, and the most essential thing happens here. So first we fire the reset 6502 function, which we'll have a look just right in a moment. But generally, the idea of this routine is to give the instruction pointer. In 6502, it's called program counter. It's in x86, it's called instruction pointer. But in 6502, it's called program counter. So the major idea behind this reset 6502, it gives the program counter an address of where to start the execution. And here it gives the address of where the KIM ROM actually starts, and we start at the address 1C22, which is the entry point into the ROM routines via reset, and we'll have a look at that at the ROM code itself, and then it just starts executing instructions and even makes a jump here. So I just wanted to make a few instructions just to make sure that my read ROM instructions are working properly, because again since the ROM is located in the prog memory, we need to use this specific macro, this pgm read byte near that is available for Arduino, and just to make sure that we do retrieve the proper addresses, so just to track the program flow a little bit before we're gonna be doing this in the infinite loop, which is gonna be the case a little bit later on. So yeah, we just step into the ROM, and then we start executing a few instructions within the ROM, and even jumping somewhere, and then we just drop because I'm just doing this within the setup, not within the loop. So yeah, hope that's clear. And now let's walk step by step through all the interesting parts. So starting from this reset 6502, so I just find this reset 6502, and here we go. So here is the first and the most important thing. So this is the way how the 6502 pro's are designed, basically. So once it gets reset, it's looking for the addresses FFFC and FFFD. So the least significant byte. Oh my God! Well, hold on a sec. The most significant byte goes to FFFC, and the least significant byte goes to FFFD. Hence this bit shift to the left by 8 bits. Yeah, not by 8 bits, but just by 8, right? So within these two addresses, we have the address stored of where we should put our program counter, and there is the address of 1C22, but it's written as 221C because of the little endian order in the little endian byte order, and the little endian in the end is for byte order. Right. So the next thing to consider is if we have a look at the interrupt request table. So IRQ interrupt. No, not this one. Yeah, no, not this one. And yeah, this one. So here I have another 1, 2, 3, 4, 5 only 6 bytes been stored in the program as well, just in order to in order to waste in RAM. So here, interrupt request table, and the address FFFC, here we have, has been mentioned, yeah, the least significant byte, I'm sorry, I said the most, probably, I don't remember. Yeah, so here we have the least significant byte, and then we have the most significant byte. Yeah, probably I just swapped them on the country, I'm sorry for that. So we have the address of 1C22, and this address, where the program counter is getting loaded into the program counter later on. So in order to grab this address, we're reading this interrupt request table, which is stored in the prog.mem. So this is the first thing to consider. And then, well, since we're not firing neither the interrupt request nor the non-maskable interrupts, so we don't care about this and this as well for now. So we just care about this 1C22. And then if we have a look at there are 2 most essential functions that whatever CPU emulator would be providing to you. Those are to read the memory, read bytes from the memory, and write bytes to the memory. So here are they. So write 6502 writes bytes to the memory, read 6502 reads bytes from the memory. So in case if we have the addressing mode that goes above the FFFA, this means that we're looking for the interrupt request table. So if the address is greater or equals than this. In this case, what we do here, so I'm using this macro pgm read byte near to reference the data stored in the prog.mem, and then the address of interrupt request table itself plus the address, but not the address itself, but just to adjust the the offset within this table itself. I do this minus FFFA, because otherwise I would need to waste really like all the 64Ks of prog.mem. I don't even have that much, because probably only have 32Ks. I'm not sure, but yeah, so that's how it goes. So here I'm reading. Here is the case when I'm reading the data from the interrupt request table, and then in case of the address starts from 1800s hexadecimal and upwards. So definitely not this one, because we would have returned already. So literally from this to this within this range, but there are only somewhere around 2Ks for the ROM. But anyway, that should be fairly enough for now. So in this case, again, we're reading the prog memory, but this time ROM, and we need to adjust the address offset here as well. So we just do this minus 1800s hexadecimal, because the first, so just to give you an idea behind this calculation, so the very first element, the very first byte in ROM, so here is the ROM, okay, so the very first byte, so the actual address of this guy is 0, so ROM indexed by 0, or ROM plus 0 in terms of offsets, but with the address we're looking for is spelled like 1800s, so we need to subtract those 1800s to make the offset appropriately, to get the proper offset. So actually minus this 1800s, and we have 0, and we reference this exact byte. Now the next thing, so once we've loaded the value of 1C22 to our program counter, we now need to we now can search for this 1C22. And here, surprisingly, well, not really, here's what we have. So this is known as the KIM entry via reset. So the resetting the CPU gets makes the program counter being loaded to 1C22, and we get exactly here. And now we're starting executing. So every step would be resulting in the execution of the following instructions. So the first instruction to consider, so we want to load the FF to the X register, and well, we could probably then add a bit more. Well, I didn't yet implement the instruction to bring the debugging information for all the registers. I'm not sure if this is actually available. Something like trace, nope, or debug. No, it's not available. But anyway, well, it doesn't matter at the moment, really. So we can try to do those tests as well. But anyway, here is the point. So here, then we go to 1C24. So once we're done with this instruction, so from this from now on, the value of the X register should be FF. Yeah, I'll probably just manually add this, or you know, I just don't want to waste the RAM for this messages. And well, obviously I could have used the program again for messages as well, but that's just extra work that I don't really want to do it. And anyway, we're not going to be using that in the production, because the KIM-1 ROM has its own mechanism for debugging. So that's the idea. But for now, we can just add a couple more serial print lines here to make sure that it's all kind of works properly. So we'll have a look. So after executing this instruction at at 1C22, here we'll print the value of the X register. So it should be FF. Then we're transferring the value within the X register to stack. So actually here we set up the stack, which is essential thing to do when we just start in the ROM routines. Then setting the value of X to SP user. I'm not sure what the SP user is. And then 1C27 here. And as I was thinking about, so this is the jump. So it jumps to the subroutine inits, and the inits subroutine is no. Let's inspect the address. So 1E, it's 1E88, and exactly indeed we have this 1E88. So let's search for 1E88. Control F. 1E88. What have I done? Oh, horrible. 1E88. All right, so here loading 1 to X register, setting the mode, and so on. So, and we stop at 1E8C. Yeah, so loading 0 to X. So yeah, all the instructions we asked it to do has been passed successfully. So yeah. Yeah, I don't really see much reason for printing the value of the X register, but just to give you an idea. So let's say serial.println, and here X register in the hexadecimal, and I just upload this just to give you an idea. So uploading, and then uploading to serial monitor. And I just clear the output and hit the reset on Arduino. And okay, so here for some reason we have the value of 0. Where exactly do I print that? Well, yeah. Obviously, that's because we didn't yet step anywhere. So yeah, let's just copy this, and here it should be FF. Yeah, now this should be 0, and then after stepping in, this should be FF. And let's make it like just to keep the order appropriate. So printing X, then the program counter, then again the program counter. And this would be like for previous. Yeah, I probably could even bring it like here. Yeah, now this should be just fine. So upload. All right. So by the time it's uploading, it wasn't available. Okay, so clear the output and reset. Yeah, and here we go. We had 0. Then after executing this 1C22, we have the FF, and that's exactly the case, because here if we search for 1C22, then yeah, LDX FF, and we have this FF in the X register as expected. So which means that the function to read the bytes from ROM seems to be working properly, which is good news. So this is it from my side in regards to this video. Yeah, and the next step would be to loop this ROM forever and trying to play around with this with a TTY mode, with the serial mode, like the mode where when you can, well, in case for the original KIM-1, you could have connected the terminal to it, serial terminal, with a monitor and the keyboard, and talk to your KIM-1 using that terminal. And the ROM has sort of an environment for that as well, so you can still like navigate through the addresses and set the values in the memory and so on. So that's going to be the next step I'm going to be trying during this development progress. Now this is really it from my side. Thanks for watching. Until the next time, and take care.